So welcome back to this channel. So in this video we are going to be handling the second part of ionic equilibria. Now this video is presented to you by Organ Base, and I advise share the video to your friends so that you can all benefit as a group. From where we had stopped, the previous video was about positive inductive effect and negative inductive effect in determining acidity and basic strength of different organic and inorganic compounds. So here we are going to be looking at mainly calculations that are involved in ionic equilibria. Now the calculations that have been compiled in this video are going to be mainly for strong acids and strong bases. But let's first derive the expressions that we are going to be using in the calculations. So looking at the derivation of expressions for acid dissociation constants, and the acid dissociation constant or acid ionization constant is represented by capital K and the subscript of A. The A represents for acid and the capital K represents for ionization constant. And you're saying and that of a base is going to be represented by Kb. Remember that the B is a subscript. So we are considering an aqueous solution of a weak binary acid. For instance, if you're having a weak binary acid, remember that an acid must donate protons according to Bronsted in the previous introductory video. So if at all an acid must donate protons, and you're saying that we are considering a weak binary acid of HX of original concentration, the concentration is going to be C moles per decimeter cubed. And then the degree of dissociation always, just like we looked at it in chemical equilibria, is represented by alpha. So we write the equation for the dissociation of this weak acid. So being weak, the arrow must be reversible. So it will give us protons in solution and also an halide. For example, if I tell it was an halogen acid. So starting with the initial concentration, this is going to be C and this is going to be 0 and this one 0, because at the beginning of the experiment we expect no product to be formed. And then to get concentration dissociated or formed, just like in chemical equilibria, you get the initial concentration, you multiply it with the dissociation constant, which is always alpha. And then after getting one of these, you use Moll ratio to find this one and this one. So according to Moll ratio, since Moll ratio is 1 to 1 to 1, if this is C alpha, also this is going to be C alpha, also this is going to be C alpha. Now when you're getting moles at equilibrium, on the reactant side we subtract. So it's going to be C minus C alpha. Now when you prime factorize out the C, you end up with C into bracket 1 minus alpha. And then on the product side, you just add. So 0 plus C alpha gives you C alpha. And then 0 plus C alpha also yields you C alpha. Now you're saying that ionization constant of an acid, just like in chemical equilibrium, is the product of the molar concentration of our products divided by the product of the molar concentration of our reactants, each raised to the appropriate power. Now the molar concentration of our products, they're all the same. They're all C alpha. So that's why you're having here C alpha squared. And then the molar concentration of the reactant at equilibrium was C into 1 minus alpha. Now if you square the reactants, concentration of the reactant, you get C squared alpha squared divided by C into 1 minus alpha. Now one of these C goes away with one of the C here. So you remain with C alpha squared divided by 1 minus alpha. So this is the ionization constant of a weak acid. This is how we get ionization constant of a weak acid when it is dissociating in solution. Now here you're saying, or proceeding that, also considering an aqueous solution of a weak binary base B of original concentration C in moles per decimeter cubed with a degree of dissociation alpha, then the equation is going to be the following. Remember that for bases, Bronsted said that they must receive a proton when they're in solution. And usually they receive a proton when they're in solution from water. So if you are told you're having a base B, which is aqueous in nature, you react it with water. Water donates a proton to it. And then we form an aqueous salt and then the hydroxyl ions. Presence of hydroxyl ions shows that this solution is basic. And then we are using a partial arrow because we are dealing with a weak base. So ionization constant of this weak base, or Kb, is going to be got by product of the molar concentrations of the products raised to the appropriate powers, which is 1 divided by the molar concentration of the reactant, which is going to be B. Now here we didn't include water because we take an assumption that water is in excess. And if water exists in excess, we don't consider it to be included in our calculation, since its quantity is assumed to remain constant before and after the reaction. The same treatment as the acid will give the expression below. If I tell you calculate them out using the equation, you are going to find that what is only going to change is going to be the ionization constant. So instead of Ka for the acid, you are going to have Kb, and they are going to have the same expression for its calculation. So that means that whenever you are asked to calculate for ionization constant of a weak base, the formula will be equal to concentration times the degree of dissociation squared, divided by 1 minus the degree of dissociation. And the degree of dissociation is always represented by alpha, and that's the symbol to represent degree of dissociation. It is used in chemical equilibria, ionic equilibria, and we shall also use it in electrochemistry. Now looking at the calculations that are going to involve ionization constant of an acid Ka, I told you A is a subscript. Now we're saying that here, the expression for the acid dissociation constant Ka for a weak acid relating concentration and the degree of dissociation is going to be given by this, just like we derived it above. Now here we are saying that, however, if at all you see that your degree of dissociation is very small, if at all the degree of dissociation is very small compared to 1, we assume that 1 minus alpha is going to be approximated to 1, because if at all we have very less degree of dissociation, let me say 0.0 something, we consider that the value is going to remain approximately 1. And therefore, we approximate this thing here in the denominator to 1. So therefore, if you're having this formula and you approximate your denominator to 1, you're going to end up with Ka being equal to C alpha squared. Now in this case, we make alpha, or the degree of dissociation, the subject. And once you make the degree of dissociation the subject, you remain with Ka divided by C. And then to remain with the degree of dissociation alone, you put roots on both sides and remain with alpha being equal to the square root of Ka, which is the ionization constant of an acid, divided by the concentration which has been given in the question. Now also here we are proceeding that, also from the procedure derived above, at equilibrium, provided that it is at equilibrium, molar concentration of an acid is always going to be equal to concentration times alpha. At equilibrium, molar concentration of an acid is always going to be equal to concentration multiplied by the degree of dissociation, which is alpha. And always remember these shortcuts because they are the most required in paper 1 when you are calculating for ionic equilibria expressions. Now continuing, we are saying that all the derived equations above can be used in calculations that are involving ionic equilibria of weak acids. And we are saying that also note that in calculations for the articulate expression, always, I've given you two expressions for calculating Ka. There's this one and this one. But for articulate expressions, you are advised always to use this formula. Don't do these approximations. However, also student who has done the approximation, in case the degree of dissociation is 0.0 something, is correct. But the one who has used the Gen expression will always be marked right. But if at all the one who has used the deduced expression has not made the assumption for alpha to be small, he may get it wrong. Now here, whenever you ask for a degree of dissociation, always use this formula. Don't go to any other formula. Degree of dissociation will be asked frequently in paper 1, and always go with this formula. And whenever you are given molar concentration of an acid and you are looking for concentration or degree of dissociation, always go with this formula. molar concentration of hydrogen ions present in that solution is equal to the concentration of that solution multiplied by the degree of dissociation, which is going to be alpha. So you're saying that the ionization constant of an acid here is going to be equal to concentration multiplied by alpha squared, and you're saying that this is going to be used depending on the value of alpha. Well, if you are told we are going to look at the examples, we are going to say that if you are using a 0.1 molar ethanoic acid, remember that ethanoic acid is a weak acid. Any organic compound that has an acid is always going to be a weak acid. So provided you're having 0.1 molar ethanoic acid and the ionization constant of the acid that has been given is this, they're asking you for the degree of dissociation. Always remember the degree of dissociation is equal to Ka, square root of Ka, which is the ionization constant of an acid, divided by the concentration of that acid. But both of them must be under a root. So substituting for Ka is 1.8 exponential negative 5 divided by the concentration, which is 0.1. And then you put your answer to at least 3 decimal places. So here it's going to be 0.0134. However, degree of dissociation can be expressed in terms of decimal places, or it can be expressed in terms of percentage. And therefore, if you're using percentage, you just multiply this number that at least to 3 decimal places and you multiply it by 100, but you're advised to write 4. Then you'll be getting 1.34%. Now here, the value of alpha is going to be very small as compared to 1. Remember the other expression that I told you. The general expression for calculating for Ka is equal to C alpha squared divided by 1 minus alpha. But we say that when the degree of dissociation is very small, we approximate the denominator to 1. And that is only obtained when you're having a number like 0.0 something. But when you're having 0. If at all you have any number here like 1, 2, 3, 4, that approximation doesn't work. So it's advisable you go with the general formula. But since here our value was small, it is 0.01. This next value after the decimal place is 0. We are free to go on with the approximation. And if you don't want to write that approximation, go with this general formula. You always get the same or related answers and they will both be marked. So making that approximation, we shall bring in this formula. And then if at all we are going to use a 0.01 molar ethanoic acid, Ka is going to remain constant. Our degree of dissociation is going to be this. Now here we are saying that the value of alpha is not very small. If you look at this here, we don't have 0.0. So we cannot approximate that Ka is equal to this because our decimal place we have got is 0.1. For the approximation to be valid, it must be 0.0. Your degree of dissociation must be 0.0. But in case it's not 0.0, then you are not supposed to approximate. But instead, you are supposed to use the general formula, which is Ka being equal to C alpha squared divided by 1 minus alpha. Now let's look at the examples that involve such calculations. So looking at number 1, we are saying that a solution was made by dissolving 1.22 grams of benzoic acid in 500 centimeters cubed of water. Part A, write the equation for the ionization of benzoic acid in the aqueous solution, hence the expression for the finding the ionization constant Ka for that acid. We also calculate the hydrogen ion concentration. I hope you remember how I told you how we calculate hydrogen ion concentration. Hydrogen ion concentration, which is represented by this, in the introduction we say that it's given by concentration multiplied by the dissociation constant, which is alpha. So part 2 we also calculate for the degree of dissociation. Now Ka for benzoic acid is always given in the question, or sometimes it's not given and you're supposed to calculate for it. Now when you're beginning this topic, I told you ionization constants are always measured in moles per decimeters cubed. This is a very common question in paper 1 because most of you present your answers without units and you get everything wrong. So writing ionic equation or the equation for the ionization of benzoic acid. Now, since it is an acid, according to Bronsted says that acids must donate protons in solution. So benzoic acid, we expect it to release hydrogen ions and they unite with water. because water is present in the aqueous solution. And once that happens, we shall form an hydroxonium ion. And we shall form a benzoate ion after benzoic acid losing its proton. Now, ionization constant of an acid is given by molar concentration of the reactant of the products, product of the molar concentration of the products divided by product of the molar concentration of the reactants, except water, because we take an assumption that water exists in excess, and if it exists in excess, we expect its quantity to remain unchanged, or we assume that its quantity is going to remain unchanged both at the beginning and at the end of the experiment. So you end up with the formula of this. Make sure that you're having square brackets. So looking at part B, we are saying that we are going to first calculate for molar mass because we want to get the number of moles present or the molar concentration of our benzoic acid since we are given mass. So we have to calculate for molar mass of benzoic acid, which is going to be 7 times 12, 6 times 1, 2 times 16. Now some of you don't write this, and this is where the marking starts. You must show how you are calculating for your relative molecular mass or molar mass. If you have said molar mass, you give it units. If you have said relative, you don't put units. So this is going to be 122 grams. So to get moles of benzoic acid present in the given volume is going to be the given mass divided by the RFM, and you are going to get 0.01 moles. Now we are going to say that these moles are therefore going to be contained in this volume. What about 1,000? Which is here. So 1,000 centimeters cubed of a solution is going to contain 1,000 multiplied by 0.01 mole divided by 500, and you are going to end up with 0.02 molar. So this is the molar concentration of benzoic acid. Now here at equilibrium in ionic chemistry, we always assume that the concentration of the reactants formed is always the same. That's why we are saying you must quote this word. This is very important because it only happens at equilibrium. So at equilibrium, molar concentration of benzoate ions is equal to molar concentration of protons or hydroxonium ions, because that happens at equilibrium. This condition, if not well stated, there's no way you can attain marks for all this. We have to first see this condition. So at equilibrium, molar concentration of benzoate ions is equal to molar concentration of protons. Now substituting, therefore we are going to have, if at all benzoate ions, substituting this formula here, we shall have since molar concentration of benzoate ions is equal to molar concentration of hydroxonium, we are going to have molar concentration of hydroxonium ions squared divided by molar concentration of the benzoic acid, which we have just calculated. Now if you're trying to make protons the subject or hydroxonium ions the subject, I told you protons are referred to, hydrogen ions are the same as hydrated hydrogen ions, and hydrated hydrogen ions, we name them as hydroxonium. So finding the molar concentration of this is like finding the molar concentration of hydrogen ions. So making molar concentration of hydroxonium ion the subject, we remain with square root of Ka times molar concentration of the benzoic acid, and then we substitute. Ka was given the question as 6.4 exponential negative 5. Molar concentration of the acid is 0.02. Now further calculations and finding square root is going to give you 1.131 exponential negative 3 moles per decimeters cubed. Now going to part B, whenever you're calculating for degree of dissociation is equal to square root of ionization constant of the acid divided by the concentration, each of them under root. So substituting we get this, and then calculating for the degree of dissociation to a minimum of 3 decimal places, you get 0.057. So it's saying that write the expression for the acid dissociation constant. Acid dissociation constant is the same as acid ionization constant of methanoic acid in aqueous solution. And part B, you'll be prompted that a 0.01 molar solution of methanoic acid is 14% dissociated. Now when they say 14% dissociated, they are meaning the degree of dissociation, because it's only the degree of dissociation that we measure in percentage. So it's the same as 14 divided by 100 at 25 degrees Celsius, which is the room temperature. And we are saying that calculate for the dissociation constant of methanoic acid at room temperature, which is 25 degrees Celsius. Now Ka for dissociation of methanoic acid, now you're supposed to write the equation for dissociation of methanoic acid first, which I missed when I was giving this solution. So since it's a weak acid, we expect it to undergo partial ionization. So you add water here, we consider Bronsted theory. You add water there and then you partial ionize the acid. So any acid, we expect it to donate protons in solution, and the protons donated react with water to form hydroxonium ions. So we shall end up with ethanoate ions. We shall end up with ethanoate ions and hydroxonium ions. So the expression will be molar concentration of the products formed raised to appropriate powers divided by molar concentration of the acid. We assume that water is excess and its concentration is going to remain constant at the beginning and the end of the equation, so there's no need to include it in our equation. Now, noting down the data given for part B, you are given the data that concentration was given as 0.01 molar. The degree of dissociation is 14%, which is the same as 14 divided by 100, and simplifying it gives you 0.14. Now, this degree of dissociation is not 0.00, it's 0.1. And they say that whenever you're having a degree of dissociation of 0.1, you use the Gen expression. You only use the other expression of Ka being equal to concentration times alpha squared. You only use this expression when you're having your degree of dissociation to be 0.0 something. But otherwise, if you're having a digit here after the decimal place, always go with this Gen expression. And I told you this Gen expression is preferably working in both situations, where you're having this and where you're having this. So Ka, after substituting, concentration is this, degree of dissociation is 0.14, we square it, and then divided by 1 minus degree of dissociation, which is 0.14. So Ka is equal to 2.28 exponential negative 4 mole per decimeters cubed. Now here you are provided with the questions. Now these questions, you write them down and then you submit in your answers, either to me directly or to your teachers, or you discuss them as a group with your fellow friends. Make sure that you link your friends to this channel so that you can discuss the work together. So question 1, write equations for ionization of ethanoic acid in water. Just like ethanoic acid is the same. I told you, according to Bronsted suggested that whenever an acid is in water, it donates protons. So write the expression for the ionization constant of ethanoic acid, and then you calculate for the degree of dissociation, provided you are given concentration and you are given ionization constant of ethanoic acid. And I told you ionization constants, I'll keep repeating this. Ionization constants are measured in moles per decimeters cubed. With calculations that are involving ionization constant of a base. Ka is for ionization constant of an acid. Kb is for ionization constant of a base. Now here you're saying that the expression for base dissociation constant Kb of a weak base relating concentration, which is C per decimeters cubed, and the degree of dissociation is going to be the same as that for an acid. What is going to vary is going to be the subscript on the ionization constant of K, which is B. And we are saying that here, however, if alpha is small as compared to 1, then we can also make the same approximation. The principles here are going to apply just like they apply for acid. Instead of protons here, we are going to have hydroxyl ions being equal to C alpha. Now here we are saying that all the derived equations above can be used in calculations only involving ionic equilibria of weak bases. This is very important. So whenever you say base, you are using Kb. Whenever they are talking about an acid, you are using Ka. That is very, very important. Now let's look at the examples. So in this example, a 0.01 molar solution of ammonia is 4% ionized. Now calculate the hydroxide ion concentration and then determine the base dissociation constant, Kb, for ammonia. I told you anything given in percentage is always degree of dissociation. Instead, Bronsted say that whenever bases are in solution, they accept protons, and what they're going to be accepting protons from is going to be water. So if water donates a proton to ammonia, which is a base, wrong state says that bases when they're in solution, they accept protons. And since it's a weak base, we expect use of partial arrows. So after water donating a proton, it remains with the only hydroxide ion, which is aqueous. And then after ammonia solution accepting a proton, it becomes ammonium ion. Now concentration given was 0.01 molar, and then the degree of dissociation is always given in percentage. So this is 4 divided by 100, which is going to yield you 0.04. Now since they ask for molar concentration of hydroxyl ions, and you have the direct expression for that, we just substitute. So molar concentration of hydroxyl ions is equal to C alpha. Concentration is 0.01, and alpha, or degree of dissociation or ionization, is 0.04. And multiplying, you end up with 4 exponential negative 4 moles per decimeter cubed. Now here, we are supposed to calculate for Kb, and the expression for calculating for Kb is given as follows. However, also although a student who would have approximated was going to be right, because the degree of dissociation here is 0.0, so the next digit after the decimal place is 0. So if student was free to use Kb is equal to 0 is equal to C alpha squared, and then you write an approximation for it. You say that since the degree of dissociation is far less than 1, therefore 1 minus alpha is approximated to be 1. But this one is the most safer decision to take, because for it is correct in both situations. So substituting for the dissociation constant 0.04, and the concentration remain with 1.67 exponential negative 5. And I told you ionization constants are measured in moles per decimeters cubed. So looking at question 2, let's write the equation for the ionization constant of methylamine in water. I told you all bases must accept a proton from water. That means that water is in charge of forming the hydroxide ion. And then whatever that compound is reacting with water, it's supposed to accept a proton. So on that compound, we expect addition of 1 hydrogen atom or ion. And then Roman number 2, we shall find the expression for the base dissociation constant, Kb, for methylamine. Then part B, the hydroxide ion concentration of 1 molar methylamine solution is going to be 0.4 mole per decimeter cubed. Then you are going to calculate the degree of dissociation, and then the base dissociation constant, Kb, for methylamine. So for part A, Roman number 1, reacting methylamine with water gives off a proton here, and then it attaches to this nitrogen atom, and then you form methylammonium ion, and then the water is going to remain as the hydroxide ion. Since it's a weak base, all organic compounds bases are weak, so you expect use of partial arrows. So this one we will do 1 mark. So Kb is given by molar concentration of the product of the molar concentration of the products, divided by product of the molar concentration of our reactant, with the exclusion of water, because I told you water is assumed to be in excess, so we expect its concentration or amount or quantity to remain the same before and after the experiment. That's why we don't include it in calculations. B, molar concentration of methylamine is 1 molar, and molar concentration of hydroxyl ions can be given by the formula of concentration times degree of dissociation, which is equal to 0.04 mole per decimeter cubed. Molar concentration of hydroxyl ions is equal to this. So we make alpha the subject. So it's going to be molar concentration of hydroxyl ions divided by concentration. So since molar concentration of hydroxyl ions was given as 0.04, we divide it by the given concentration, which is 1. You are going to end up with 0.04. Now notice that here, the degree of dissociation does not have units. It only has units when you express it in percentage and you put it percentage. But when you're putting it in decimal places, it does not have units. So Roman number 2, from Kb, from the general expression, substituting for degree of dissociation, we are going to end up with our Kb as 1.667 exponential negative 3. Now here, since our degree of dissociation is 0.0, also student who could have used Kb being equal to C alpha squared would have been correct. So let's go to the auto-ionization or self-ionization of water. Now, pure water is a weak electrolyte due to the slight dissociation into oxonium. Oxonium ion can also be called hydroxonium, and then the hydroxide ions. So water, it undergoes partial ionization to form the hydroxide ions, oxonium ions, and then hydroxide ions. So hydroxonium ions and hydroxide ions are formed. So from the law of mass action, we can get the ionization constant of water. It can either be written as K, or someone can write here W to show that you are getting ionization constant of water. It is represented by K with a subscript of W. So molar concentration of your products divided by molar concentration of your reactants. And that since the degree of dissociation of pure water is very small, approximately 18 exponential negative 10, and the molar concentration of water is so very large as compared to that of the hydroxonium ions and hydroxyl ions, molar concentration of water is taken to be a constant. Now here what this statement is meaning is that this expression initially in the first step it was divided by molar concentration of water, but we expect water or concentration of water or the amount of water to be existing in very large amounts, and if that's the case, if something is existing in large amounts, we expect it in chemical reactions, its amount or its concentration to not only be slightly affected, but to remain the same. So that's why we don't include it in our expression. Therefore, remain with ionization constant of water, which is represented by Kw. The W is for water, the K is for ionization constant, as molar concentration of the hydroxonium ions multiplied by the molar concentration of the hydroxide ions. Now here we're saying that the constant Kw is called the ionic product of water, or ionization constant of water, or ionic product of water. Now we're saying that at room temperature, which is always 25 degrees Celsius, 1 decimeter cubed of water contains approximately 1 exponential negative 7 moles of both hydrogen ions and hydroxyl ions. So we expect hydrogen ions to exist in this concentration, and we expect hydroxyl ions to exist in this concentration. So we are having Kw of water. If you are to substitute in this formula, molar concentration of hydrogen ions or hydrated hydrogen ions is going to exist like this. And molar concentration of hydroxyl ions is the same. That's why we are putting here a squared. And once you do the math, this squared is going to multiply this and this. So you're going to remain with the ionic product of water or ionization constant of water to be 1.0 exponential negative 14. Because 2 times negative 7, you end up with negative 14. Also, the units are squared. So squaring the units is going to be mole squared per decimeter, decimeters per negative 6. Now here we are saying that since the dissociation of water is going to be endothermic, the ionic product of water Kw increases with increase in temperature. However, the value at which 25 degrees Celsius is commonly used, since most experiments are going to be carried out at that temperature. So oftenly you are going to find this temperature being stated in the questions that you are going to be given, showing you that the experimental data that you are being given to calculate for the different constants or ionization constants, that experiment was done at room temperature. Always remember that room temperature is 25 degrees Celsius. So temperature at 10 degrees Celsius, ionic product of water is this, 2.9 exponential negative 15. At room temperature, ionic product of water is 1.0 exponential negative 14, which is the one which is acceptable. That's why it's in white. And then at 50 degrees Celsius, ionic product of water is going to be 5.47 exponential negative 14. Now this is not relevant and you're not going to be asked for it anywhere, but you must know the one for room temperature. The concept of pH at this extent. Now we're saying that here, pH is going to be the negative logarithm to base 10 of the hydrogen ion concentration in moles per liter of any given solution. This definition is highly asked in chemistry, especially paper 1 mocks. pH is the negative logarithm. It is represented by a formula. Whenever you're told to calculate for pH, always remember its definition from the formula. That's going to be the negative logarithm to base 10 of the hydrogen ion concentration that is present in moles per liter of any given solution. Always remember that. Now you're saying that since at room temperature, 1 decimeter cubed of water contains approximately 1.0 exponential negative 7 moles of both hydrogen ions. Here we are only considering hydrogen ions. Remember that the concentration of hydrogen ions is the same as hydroxyl ions. That's why they are all 1.0 exponential negative 7. Now since the concentration of hydrogen ions is 1.0 exponential negative 7, we come and we substitute it in this formula for calculating pH of water. Since water contains a molar concentration of hydrogen ions to be 1.0 exponential negative 7, and if you put this in your calculator, you end up with 7, showing you that the pH of water is 7, and according to the pH scale, 7 is a neutral level. That means that water is neutral. Now you're saying that the higher the concentration of hydrogen ions, the lower the pH. That means that the higher the acidity, the lower the pH, because acidity is determined by the concentration of hydrogen ions. That means that the higher the concentration of hydrogen ions, the higher the acidity, and the lower the pH. Hence, the stronger the acid. And you're saying that the pH of an aqueous solution of an acid or base is going to depend on the concentration and the degree of ionization of any base or any acid or any weak acid or any weak base. Now we are saying that pH is the same as negative logarithm to base 10 of the hydrogen ion concentration in moles per liter of a solution. What about pOH? So pOH is the opposite. What varies is going to be the hydroxyl, but it's also going to be negative logarithm to base 10 of the hydroxyl ion concentration in moles per liter of the hydroxyl ion concentration of any solution. Now you're saying that pKw is going to be related to the ionic product of water, and you're going to say that pKw, P is like representing negative logarithm to base 10, and then the Kw, which is the ionic product of water. The above data given, we are going to summarize that therefore, from the ionic product of water, Kw, remember that we gave this formula as the ionic product of water. So let's try to introduce negative logarithm to base 10 on both sides. If you introduce negative logarithm to base 10 on this side, and you also introduce it on this side, we are going to separate accordingly. But when you're separating, remember that this negative is going to be shared on this one and this one. Product in logarithm means addition, so we separate them by addition, but the negative must be shared on both the hydroxonium ion concentration and the hydroxyl ion concentration. But remember that we said that negative logarithm to base 10 is the same as P, or is represented as small p in chemistry. So it's going to be P, ionic product of water, to be equal to pH plus pOH. So this is a very important expression because you are going to be using it everywhere in the calculations that you are going to dig into. So always remember that Kw is going to be equal to pH plus pOH. That means that if you want pH from here, you can make pH the subject by saying that pH is going to be equal to pKw minus pOH. And pKw, remember that Kw, or ionic product of water, we got it as 1.0 exponential negative 14. Now if you put it in negative logarithm to base 10, you end up with 14. Therefore, since pKw is 14, that means that 14 is equal to pH plus pOH. Now see that the above equation can be used for aqueous solutions including water at room temperature which is always 25 degrees Celsius. Now let's look at the calculations that are going to be involving what you have derived, pH, pOH, and pKw, for strong acids and for strong bases. And in the next video, we shall be looking at how you are going to be using those expressions for weak acids and for weak bases. So let's start with strong acids. And you're saying that for strong acids are completely ionized in aqueous solution. Therefore, pH is going to be equal to P is represent negative logarithm. The H represents molar concentration of hydrogen ions. So pH is given as negative logarithm to base 10 of the molar concentration of hydrogen ions in moles per liter of any solution. And it's saying that a solution is found by dissolving 1120 centimeters cubed of hydrogen chloride in 500 centimeters cubed of water at standard temperature and pressure. Calculate the pH of that solution. Now here, remember that at standard temperature and pressure, it means that hydrogen chloride gas dissolves in water to form HCl. And at room temperature or standard temperature, STP, it's always 22. We assume that 22,400 centimeters cubed of a solution contain 1 mole of any compound, like hydrogen chloride gas, of any gas. So we assume that this one contains 22,400 centimeters cubed of any matter contains 1 mole of HCl, which is hydrogen chloride at STP. Then what about the given volume, which was given as 1120 centimeters cubed, will contain how many moles of hydrogen chloride? So it's going to, when you do the calculation and put it in the formula in the calculator, you're going to get 0.05 mole of hydrogen chloride at STP. Now these moles here were dissolved in which solution? So these moles here were contained in a solution of 500. Then what about 1000? Because we want molar concentration of the acid. Now remember that for strong acids, they fully ionize. So strong acids, since they fully ionize, we expect you to be using a full arrow. So HCl fully ionizes to give you hydrogen ions and chloride ions. Now we say that to get pH, now that means that for full ionization, it's better you consider mole ratios. So since this is full ionization, and we can consider mole ratio of 1 to 1 to 1. So molar concentration of the HCl is the same as molar concentration of the hydrogen ions, and at the same time it's the same as molar concentration of the chloride ions, because the molar concentration is the same, or the mole ratio is the same. And we have calculated the molar concentration of the acid to be 0.1. And pH is given as negative logarithm to base 10 of the hydrogen ion concentration in moles per liter of any solution. So once you do the substitution, now when you substitute, make sure that you don't use the square brackets again. It will be negative logarithm to base 10 of 0.1, and you're going to end up with 1 as your answer. So pH for this solution is 1, showing that it's highly acidic. So looking at option 2, or number 2, you are prompted that 25 centimeters cubed of a 0.05 molar sulfuric acid was added to 750 centimeters cubed of water. Now you are prompted to calculate for the pH of the resultant solution. Now finding the moles of the sulfuric acid that were present here, we are going to say that 1000 contain this. What about the 25 that we used? So 1000 centimeters cubed contain this. What about the 25 centimeters cubed? Contain which moles? Now these are the moles that we added to water, and we added them to 750 centimeters cubed of water. So 750 centimeters cubed of water, we expect them to contain these moles. But we need to get the total volume, because we got 25 centimeters cubed of the acid and we added it to 750 centimeters cubed of water. So resultant volume is going to be 25 plus 750 to end up with 775 centimeters cubed. That means that the 775 centimeters cubed is the total volume of both the acid and water that contain these moles. Then let's get the molar concentration. So here we are saying that here 775 centimeters cubed of a solution contains 0.0125 moles of sulfuric acid. Then what about 1000? Because we want molar concentration. 1000 is going to contain 1000 multiplied by 0.025 divided by 775 moles of sulfuric acid, and then you are going to end up with this concentration of the acid. Now here, since also sulfuric acid is a strong acid, it fully ionizes. After fully ionizing it, make sure that you balance the acid, because this is a dibasic acid. So balancing, we shall put here 2 on the hydrogen ions. Now here, since mole ratio is 1 to 2, that means that the molar concentration, like I quoted it here, mole ratio of sulfuric acid to protons is 1 to 2. Now notice that we are only going to be considering mole ratio only in strong acids and strong bases. That's why I divided these videos. Make sure that you first understand this concept for molar concept that is going to be for strong acids that fully ionizes. But if you go to weak bases and weak acids, we are not going to be considering mole ratios because they partially ionize. So therefore, molar concentration of the hydrogen ions or of the acid is going to be, of the hydrogen ions present in concentrated sulfuric acid is going to be twice the molar concentration of concentrated sulfuric acid. Now, some of you may use first principles to come up with this. Here, I just decided to shorten the working. So it's going to be 2 multiplied by 0.0161, and you are going to end up with 0.0322 molar concentration. Now, pH is given by negative logarithm to base 10 of the hydrogen ion concentration. And substituting for the hydrogen ion concentration that you get is going to be negative logarithm to base 10 of 0.0322 molar, which is going to give you 1.5. And pH has no units. You leave it like that, and you make sure that it is at least to 2 decimal places, if at all the answer is not definite. Now let's look at question 3. Question 3 is prompting you to calculate for the mass of hydrogen chloride required per liter to form a solution with pH 3. Now here is going to be reversing math. So pH is given by negative logarithm to base 10 of the hydrogen ion concentration in moles per liter of any given solution. Now they gave us pH and we don't have molar concentration of the hydrogen ion. So we do reverse. We shall divide through by negative to get this, and we make log 10 the subject. So log 10 of the hydrogen ion concentration is going to be equal to negative 3. And then in math, we say that you take this 10 here and it becomes, the 3 becomes a power of the 10 of the base on the log. So molar concentration of hydrogen gives us 10 to the power negative 3, which is the same as 0.01 molar. Now, since we have got molar concentration of the protons, we can write out the full ionization of the acid, because hydrogen chloride dissolves in water to give HCl. That's why you're having here aqueous. So hydrogen chloride dissociates fully because it forms a strong acid. You must use a full arrow to give us hydrogen ions and then chloride ions. Now you're seeing that since the mole ratio of protons and hydrogen chloride is 1 to 1, that means that molar concentration of the acid is the same as molar concentration of the protons, which we have got it as 0.01 molar. And therefore we can get molar mass of the acid since they want concentration in mass or in mass per liter. So you have to convert our moles into mass. But remember that RFM is equal to 1 mole. Then what about, that means that 1 mole contains the RFM. What about the moles that we are having, which are already in terms of per liter? So HCl is going to be got by 1 times 1 to get 1 plus 35.5 times 1. And you're going to end up with 36.5. When you say molar mass, you put units as grams. When you say relative, don't put units. So mass of HCl required is going to be equal to the RFM multiplied by the concentration or the moles you are having. And the mass that is required is going to be 0.365 grams. Now let's look at question 4, which is prompting you to calculate for the pH of a solution formed by mixing 80 cm cubed of water of 0.1 molar sulfuric acid with 120 cm cubed of 0.1 molar potassium hydroxide. Let's start with getting moles present in sulfuric acid. So 1000 contains 0.1. What about 80? Is going to give you 0.08 moles. 1000 contains 0.1. What about 120 of potassium hydroxide that we used? And it's going to give you 0.012. Now we need to write the equation to show the neutralization reaction. It's a dibasic acid reacting with a monobasic base. We form the mole ratio is going to be 1 to 2. So 2 moles of potassium hydroxide reacted with 1 mole of the acid. Then what about the moles of potassium hydroxide that we used? It's going to react to give us how many moles? So it gives us 0.06 moles of sulfuric acid. So that means that out of the 0.08 moles of sulfuric acid that were present, only 0.06 moles of sulfuric acid reacted. Then we are supposed to get the moles of excess acid because they are the ones that determine pH of our solution. The moles that are of the acid present in excess are the ones that determine pH of our solution. So we do that by getting 0.08 minus 0.06, and then you are going to get these moles. But we need to understand that these moles of the acid are present in which volume. Remember that we added volumes of 80 for the acid and 120 for potassium hydroxide. So we need to understand which total volume are these moles of the acid in, so that we can get molar concentration of those moles of the protons or acid. So as you have said, the total volume of the solution in which these moles are present is going to be 80 plus 120, and it's going to give you 200 centimeters cubed. So you're going to be saying that 200 centimeters cubed contain these moles of sulfuric acid. Then what about 1000, so that you can get molar concentration of the acid? So 200 contains 0.02 moles of the acid. What about 1000, so that you can get molar concentration, which is going to be 0.02 multiplied by 1000 divided by 200, and you're going to end up with 0.01 molar of our sulfuric acid. Now, since in the formula for pH we only need molar concentration of hydrogen ions, we have to first write out the ionization of our concentrated acid. So sulfuric acid fully ionizes, that's why you're seeing a full arrow, to give us 2 protons when it's balanced, 2 protons plus a sulfate ion. So mole ratio here is going to be 1 to 2 between sulfuric acid and then the hydrogen ion that we need to calculate for our pH. That means that molar concentration of hydrogen ions according to first principles. If I tell you calculate it out using first principles, here I shortened it so that I believe that you have done some good practice in your practicals. So it's going to be 2 multiplied by the molar concentration of your acid, which is 2 times 0.01, and then you are going to end up with 0.02 molar as the molar concentration of the protons. Now pH is given by negative logarithm to base 10 of the hydrogen ion concentration, and if that's the case, you just have to substitute, and you're going to end up with pH being equal to negative logarithm to base 10 of 0.02, and the 0.02 is going to be the concentration of the hydrogen ions or the protons. And after substituting it in the calculator, you're going to end up with 1.7 as your pH. That means that your solution or your resultant solution was acidic. Now I told you, you can write pH in terms of 1 decimal places, 1 dp, or if you want to be more accurate, you can put it to maximally 2 dps. So if you have to look at the questions that can be involved or engaged here, we are going to be looking at the calculation of pH over 0.005 molar sulfuric acid. And these are your sample questions. Try them out and submit in your answers. Either discuss them as a group or you can submit them to me directly. So number 1, calculate the pH of a 0.005 molar sulfuric acid. And number 2, a solution of a pH of 5.5. A solution has a pH of 5.5. So here you are being given pH and you are told to calculate its hydrogen ion concentration, which you have already done an example about it, reversing pH. The second chapter, we are going to be looking at strong bases. We have been looking at strong acids. So let's look at the calculation for strong bases. Now here, we are saying that strong bases are going to be completely ionized in solution. And by this, we are meaning for something to be completely ionized in solution, it means that we are going to be using 4 arrows. Now, we are saying that strong bases are completely ionized in solution to produce hydroxyl ions in the solution, but not hydrogen ions. We don't expect a base to produce hydrogen ions, but we expect it to produce hydroxyl ions. Therefore, we are saying that the hydrogen ion concentration is obtained first using ionic product expression. Remember that in pH, you must have molar concentration of hydrogen ions, and it's what you're going to be asked for. But when you're dealing with bases, you're always going to have OH. But remember that ionic product of water is equal to molar concentration of hydroxonium ions. But hydroxonium ions can also be written as hydrogen ions because they are just hydrated hydrogen ions multiplied by molar concentration of hydroxyl ions. So we shall be using this expression to guide us on how to find molar concentration of hydrogen ions, provided we have molar concentration of hydroxyl ions. Ionic product of water is also known. Now you're saying that pH therefore after obtaining this is going to be equal to negative logarithm to base 10 of the hydrogen ion concentration in moles per liter of any solution. Now you're saying that O, you can use the given formula, like the derived formula that we came up with, that pH plus pOH is equal to pKW. That means that here you have to first calculate for pOH, and pOH is the same as P represents negative logarithm to base 10, and the OH is going to be the molar concentration of the hydroxyl ions. And then pKW is the same as negative logarithm to base 10 of the ionic product of water, which is 1.0 exponential negative 14. So making pH the subject, you are going to end up with P potential of an ionic product of water minus pOH. So let's look at the examples under that. So number 1, calculate the pH of this solution made by dissolving 1.5 grams of potassium hydroxide in 250 centimeters cubed of water at 25 degrees Celsius. So starting with the molar mass of potassium hydroxide is going to be 39, which is for potassium, 16, which is for oxygen, and then plus 1, which is for hydrogen. I told you this is very important, showing how you are getting your relative molecular mass. Don't just do everything on the calculator and you just put them there. So molar mass for potassium hydroxide is 56, and the reason why we are doing this is because we are given mass and we want moles or molar concentration. So to get moles, you have to get RFM. And we get moles for potassium hydroxide by getting given mass divided by the RFM or molar mass, and you are going to get 0.0268. Make sure that most of the things that you're using, they are in 4 decimal places if at all you're proceeding with your calculations. So these moles are in which volume? We are told that these moles were dissolved in 250 centimeters cubed of water. Then what about the molar concentration? So if 250 centimeters cubed of a solution contain these moles, we want molar concentration of potassium hydroxide. So that means that we need to get moles in 1,000 centimeters cubed, which is going to be 1,000 multiplied by 0.0268 divided by 250, and then you're going to end up with 0.1072 molar. Potassium hydroxide fully ionizes, and when it fully ionizes, it forms potassium ions and hydroxyl ions. Now, molar concentration of potassium hydroxide is the same as molar concentration of hydroxide ions, and this is because this is a full ionization with a full arrow, so we can consider mole ratio 1 to 1 to 1. So molar concentration of hydroxide ions is going to be the molar concentration of potassium hydroxide, which we have calculated to be 0.1072 molar. Now I told you there are 2 ways. You can either find pOH and use the other expression that we derived, or you can go with the calculation approach by saying Kw is equal to molar concentration of hydrogen ions times molar concentration of hydroxyl ions. And then you make molar concentration of hydrogen ions the subject. So you have Kw divided by molar concentration of hydroxyl ions, which you already have. Kw is always constant, which is 1 exponential negative 14. And molar concentration of hydroxyl ions, you got it as 0.1072. And then you're going to have your answer as 9.328 exponential negative 14 moles per decimeters cubed. So pH is equal to negative logarithm to base 10 of the hydrogen ion concentration in moles per liter of any solution. So substituting, you remove the square brackets and introduce the curved brackets. And then you put the value that you have got. And putting everything in the calculator, you're going to end up with your pH being 13. So going to number 2, we are saying that at 0 degrees Celsius, any product of water is going to be 1.14 exponential negative 15 moles squared per decimeters per negative 6. Now calculate for pKW for ionic product of water, potential of ionic product of water at 0 degrees Celsius, and then the pH at 0 degrees Celsius over 0.1 molar solution of sodium hydroxide. Now if that's the case, pKW is the same as negative logarithm to base 10 of the ionic product of water. So substituting for ionic product of water at that instant, we are going to end up with 14.94. I told you maximally that pH must be to a minimum of potential. Whenever you are seeing this P attached to anything, it must be to a minimum of 2 decimal places. So going to number 2, we first write the dissociation of sodium hydroxide. Since it's a strong base, it fully ionizes to form sodium ions and hydroxyl ions. So since mole ratio is 1 to 1, molar concentration of sodium hydroxide is the same as molar concentration of hydroxyl ions, which is the same as 0.01. So here we can calculate for pOH, which is the same as negative logarithm to base 10 of the hydroxide ion concentration. And substituting for this, we shall have negative logarithm to base 10 of 0.01. So you end up with 2. Now using the formula for pKw being equal to pH minus plus pOH, if you make pH the subject here, we shall remain with pH being equal to pKw minus pOH. Then you remain with 14.94 because we had already calculated for pKw. So you remain with 14.94 less 2, so that you are getting 12.94. 3, 25 centimeters cubed over 0.3 molar sodium hydroxide was added to 225 centimeters cubed of water, and this was done at room temperature. That means that the ionic product of water is 1.0 exponential negative 14. Always note that whenever you're having this temperature. So calculate for the pH of the solution that is being formed. So moles of sodium hydroxide, we have to first calculate for the moles in this statement. So 1000 contains 0.3, what about 25 centimeters cubed? They are going to give us 0.075 moles of sodium hydroxide. Now these moles here were added to water. Now here you are seeing that we are getting a given volume of sodium hydroxide and we are adding it to another volume of water. So you have to get total volume to determine the total volume in which these moles are contained. So it's going to be 25 plus the 225 centimeters cubed of water to give us a total volume of 250. That means that 250 contain these moles. And what about the 1000? So 250 centimeters cubed of a solution contains 0.0075 moles of sodium hydroxide. What about 1000? So that we can get molar concentration of our base. So it's going to be 0.03 molar concentration of sodium hydroxide. Now, since sodium hydroxide is a strong base, it fully ionizes to form sodium ions and hydroxyl ions, but our interest is the hydroxide ions. So we take mole ratio between sodium hydroxide and hydroxyl ions, and mole ratio is 1 to 1. And we only consider mole ratio because it's a full ionization. We are using full arrows. So mole ratio of sodium hydroxide to hydroxide ions is 1 to 1. Therefore, molar concentration of sodium hydroxide is the same as molar concentration of hydroxide ions, which is equal to 0.03 molar. So from ionic product of water being equal to molar concentration of hydrogen ions times molar concentration of hydroxyl ions, we make molar concentration of hydrogen ions the subject. And once we do so, I told you here you can calculate for pOH. pKw is known as 14. You don't have to calculate it. And then you can use that pathway. You use the other derived expression to find pH. But here, let's go with this first approach. So from any product of water being equal to molar concentration of hydrogen ions times molar concentration of hydroxyl ions, we make molar concentration of hydrogen ion the subject. Any product of water is given as 1 exponential negative 14 divided by molar concentration of hydroxide ions, which you got it as 0.03 molar. So you're going to be getting 3.333 exponential negative 13 molar as the concentration in moles per liter of hydrogen ion concentration. So pH is equal to negative logarithm to base 10 of the hydrogen ion concentration of any solution. And substituting for the hydrogen ion concentration, we remove the square brackets and then we retain the curved brackets. So you remain with 12.5 as your pH. Now, so the logistics, let's go through this quickly. Moles of HCl is going to be attained as 0.08. Moles of potassium hydroxide is going to be got as 0.012 moles. So reaction for neutralization is going to be HCl reacting with potassium hydroxide. Both of them are mono to form potassium chloride and water. And mole ratio is going to be 1 to 1. That means that moles of the acid reacted are going to be the same as moles of the potassium hydroxide reacted. Now, since moles of the acid were less, we expect that we have excess amounts of the hydroxide. So we expect our solution to be alkaline. So we get excess amounts of the hydroxide by reducing the number of moles. We assume that all the acid reacted. So we get the total number of moles of potassium hydroxide, we less the concentration of the acid, or the number of moles of the acid, to get the number of moles of potassium hydroxide present in excess. Then to get the total volume of the solution, you get the volume of the hydroxide and also get the volume of the acid to get the total volume, because they're the ones which contain these excess moles. So 200 centimeters cubed of a solution contains 0.004 moles of potassium hydroxide. What about 1,000? So that we can get concentration. And after getting concentration, we write an equation for the full ionization of our strong base. Therefore, you must use a full arrow. So you're going to get potassium ions and hydroxide ions. So since molar concentration is 1:1, molar concentration of potassium hydroxide is the same as molar concentration of hydroxide ions. And you're going to get 0.02 molar. So POH is equal to negative logarithm to base 10 of hydroxide ion concentration. And substituting for that, you're going to get 1.699. And pH from the derived expression is equal to pKw, but pKw is the same as 14 minus POH, which you have already calculated. So 14 minus 1.699 is you're going to derive 12.3 as your pH of that solution. So let's look at the questions. Now question 1, calculate the pH of a solution made by dissolving 4 grams of sodium hydroxide in 1 liter of water present at room temperature. I told you room temperature will tell you that your pKw is going to be 14, or your ionic product of water is going to be 1 exponential negative 14. Relationship between acid ionization constant and the base ionization constant for the acid to base conjugate. Now we are saying that considering the acid to base conjugate pair of ammonium ion and ammonia in aqueous solution, the equilibria involved for the acid, which is ammonium ion, and its base, ammonia, are going to be as follows. So for the ammonium ion reacting with water, we expect it to release a proton to water because it's acidic. So after releasing it to water, since there are weak bases, we expect use of partial arrows. We shall get ammonia, and then you also get hydroxonium ions. However, when you're having a weak base reacting in aqueous solution, we expect bases to accept protons. So we are forming ammonium ions and hydroxide ions. However, for the first equilibrium, Ka is going to be given by this for the first reaction. And then for the second reaction, Kb is going to be given by this. This is a conjugate acid, this is a base. So acids always release protons, bases accept protons. So the expressions are going to be represented as follows. Now if you say that equation 1, if you multiply equation 1 and you multiply equation 2, we are going to get Ka. We shall say that Ka times Kb, which is written like this, is going to be equal to the expression of Ka multiplied with the expression of Kb. Now once we do so, we shall find out that molar concentration of ammonia here is going to cross and here is going to cross, and molar concentration of ammonium ions is going to cross here and is going to cross here. So you are going to remain with molar concentration of hydroxide ions times molar concentration of hydroxonium ions, which is represented as follows. Now when you remain with molar concentration of hydroxonium ions times molar concentration of hydroxyl ions, remember that we said that the ionic product of water is given by that formula. So replace the molar concentration of hydroxonium ions times molar concentration of hydroxyl ions with Kw, which is the ionic product of water. So implying that ionization constant of an acid multiplied with the ionization constant of a base, they give you ionic product of water. So always remember this, that Kw is always going to be equal to Ka multiplied by Kb. So that's the takeaway here. Expression of pH for weak acids and weak bases. So you're saying that weak acids are not completely dissociated, even in very dilute solutions. The expression molar concentration of hydrogen ions being equal to concentration times dissociation constant alpha can be used to get the hydrogen ion concentration, or the hydrogen ion concentration can be obtained from the pH expression, which is given by pH being equal to negative logarithm to base 10 of the hydrated ion concentration. This one can either be hydroxonium ions or it can be hydrogen ions. Now you're saying that weak bases are also not completely dissociated. That means that you can use this expression for calculating their concentration or degree of dissociation to get hydroxyl ion concentration and the hydrogen ion concentration. And they're saying that the following can be got from the ionic product of water. So from the ionic product of water is given by molar concentration of the hydrogen ions or hydroxonium ions times molar concentration of hydroxyl ions. Now if you make molar concentration of hydrogen ions the subject, you remain with the ionic product of water, Kw, divided by molar concentration of hydroxyl ions. Then the pH is going to be given by the formula for finding pH remains constant as negative logarithm to base 10 of the hydroxonium ion concentration or the hydrogen ion concentration. Or simply you can use the derived expression that pH plus pOH is equal to pKw. And remember that pOH is given as negative logarithm to base 10 of the hydroxide ion concentration. pKw is got as negative logarithm to base 10 of ionic product of water. And therefore, if you make pH the subject in this equation, you end up with this expression, that pH being equal to pKw, which is always 14 at room temperature, minus pOH, which you always have calculated. End of this video as the second ionic equilibria video. Now we shall be proceeding the third video with calculations involving Ka, Kb, and Kw, but here we are going to be dealing with weak acids and weak bases, as they are the mostly commonly examined questions in the question banks. Now you advise to subscribe to the channel, share the video to your friends, and like the video so that it can all benefit others.